The first major big idea we looked at had to do with structure. What's holding things together? Structure is governed by one thing, Coulombs Law. Sometimes they call things having a strong or a weak Coulombic attraction. Okay. Coulombs Law is very simple. It says that the force of attraction between two charged particles is going to be equal to the value of that charge divided by the distance those charges are from one another. So, for example, if you had a positive charge and you had a negative charge here, they're going to be drawn towards one another. The negative is going to be pulled towards the positive and vice versa. If in a new situation, this positive was 2 plus and this was negative, that force of attraction would increase because you increase the numerator. Okay. Conversely, if you have two charged particles being attracted to one another and you increase their distance, okay, you get them farther from one another, the attraction is going to be less. So how does that play out in what we've been doing in class? So let's take a look at a molecule. We're an atom like sodium. Sodium has 11 protons in its nucleus. That's equivalent to this charge species here. And it's got 3 energy levels. In the first one, there's 1s2. In the second one, there's 1s2 and 2p6. 2, 3, 4, 5, 6. And then there's 3s1. Okay? And this is an electron. So just like this negative is attracted to this positive, this negative here is attracted to this positive. Okay? The amount of energy required to remove it is called the ionization energy. Okay? So there's 2 ways to make that ionization energy stronger. One way is moving to the right on the periodic table. That would increase this nuclear charge, moving over to magnesium where we have 12 protons. That would cause a greater pull on this electron, increasing the Coulombic attraction, thus making it harder to remove that electron. This effectively decreases the atomic radius. Okay. Another way is to move down on the periodic table. By moving down on the periodic table, we put the electron out in a further energy level. Okay. In this case, although we are increasing the number of protons here, we're increasing the shielding, effectively increasing the distance from the nucleus. This is going to decrease the Coulombic attraction, decreasing the ionization energy, and subsequently increasing the atomic radius. So with structure, get those charges closer together, make them bigger, it's going to be greater. Get them further apart, make them smaller, it's going to be weak. In chemistry, we experience Coulombic attraction mainly by the energy required to pluck off an electron. The next thing we talked in the year was something after properties, after structure, we moved on to properties. Okay. Properties referring to how hard it is to boil something, how much vapor it releases, how strong the bonds are, basically the characteristics of matter itself. And when we talk about properties, we really have to tease out the difference between intermolecular forces and intramolecular forces. So if we had a compound, okay, this is a non-polar compound because it's symmetrical, you never just have one. And the force in between here, the intermolecular force, this is called a London dispersion force. This is the IMF force. We also have another force here, the intramolecular force. If we had a polar substance, a substance that is asymmetrical, okay, dipoles exist, with the electrons being closer to the more electronegative element. And they line up accordingly. Oops. So there's always going to be this dipole-dipole bond, or London bond. But now, because we have a dipole, a negative and a positive, we get another intermolecular force this being a London dispersion force, and this being the dipole-dipole force. Okay. So when you boil something, and this is a very important part, okay, the intermolecular forces are directly proportional to the boiling point. Okay. So when you boil something, you are not changing this bond. For example, I could add 5 bonds right there, and it wouldn't change the boiling point, because when you boil, you're breaking this bond, not this bond. Also, as the IMFs increase, and this amount here, this intermolecular force increases, the vapor pressure is going to decrease. There's less vapor in the air because less intermolecular forces have been broken. Now, it's tricky when you have a tie between intermolecular forces, and let's look at a situation here. Here we have Ni3 and we have NCl3. Now, if you were to do the Lewis structures out for both of these, you would see that they're both polar, okay? Which means they both have dipole intermolecular forces and London. Well, the question now remains, which one has a higher boiling point? Okay? And it turns out that it's Ni3. And it's because we look at the things that strengthen each. So in this case, the dipole-dipole is always strengthened by something called polarizability. We'll get to that in a sec. Blech. And that's wrong. The dipole-dipole is always strengthened by something we call hydrogen bonding. And the London is strengthened by something that we call polarizability. Okay? So in this case, you have hydrogen bonding if you have hydrogen connected to nitrogen, oxygen, or fluorine. That's going to create a really big dipole, causing this connection here to be really strong. Okay? We don't have that here. So we need to look to London. London is strengthened by polarizability, and because iodine is a larger atom than Cl, iodine's going to be more lopsided from time to time. Most of the time it's going to be a circle, but sometimes it might be more lopsided, and we call that lopsided tendency polarizability, which increases the overall boiling point. So in this case, Ni3 is it. Now let's look at a different situation here. Let's say we had NH3 and NF3. In this case, a very similar situation. They're both polar. Okay? So they both have London and dipole-dipole. Well, in this case, though, this has hydrogen bonding. So the dipole-dipole is strengthened. So when we're looking at properties, it relates to things like boiling points and melting points, but really teasing out this difference between the force here, the intramolecular force, the one related to bond energy, and the intermolecular force, or the IMF. We strengthen IMF by strengthening dipole-dipole through hydrogen bonding and strengthening London through polarizability. Now, it's really easy to get polarizability mixed up with ionization energy. Okay? So you can think about it this way. The lower the ionization energy, the bigger the radius, and the more the polarizability. Next, we moved on to reactions. So I'm just going to focus on 3 major reactions, but what we have here is we have bonds actually being broken in the molecule. Okay. So first category we talked about are those double replacement reactions, and I'm going to actually draw 3 different beaker diagrams because it turns out these beaker diagrams are hell of important. All right. So in the first kind of double replacement reaction, we have an acid-base, typical acid-base with something like hydrogen and Cl mixing with something like sodium and hydroxide. In this case, the sodium is going to mix with the Cl, stay ionized, and the water is going to form as a liquid. Okay? You're going to see a drop in conductivity because the ions are going towards the water. This is a titration, in this case, strong acid, strong base titration. You can also have a different one like this where you have the acid, let's say, we'll use Cl again, but in this case we have it mixed with a carbonate. Okay, and in this case, you're still going to make the Na plus and the Cl. You have a little excess Na here. But when that Cl goes with the H, we make H2O, and you make CO2 gas. That's a really common thing, and that's going to bubble off. Okay, that's going to have an overall positive change in entropy. And then you can have one in which you have no hydrogen at all. Okay, and this would be a precipitation reaction. So let's say we have NaCl mixing with AgNO3. These are going to mix, and anyone who has a nitrate or anyone who has a alkali metal like sodium, lithium, potassium, etc., or both, are always going to be in ion form. These things always have a very high KSP, meaning they love to be broken into ions, and the precipitate is going to clump up here in the bottom, and this is something with a very low KSP. Okay, so there's your double replacement reactions. Let's go ahead and look at the next category that we looked at, which was combustion reactions. In a combustion reaction, you always have something, carbon and hydrogen. Well, actually, you always have something plus O2 goes to heat, right? That's really what's going on in a combustion reaction. Combustion of hydrocarbons always is some carbon, some hydrogen, and sometimes oxygen with O2 going to CO2 plus H2O, okay, plus heat, and I'm going to do that in red. We'll do plus H in this case. Okay. So some characteristics of this, they're exothermic. The energy required to break the bonds is less than the energy you get when you form the bonds. And the final type of reaction that we talked about was those in which we would create a battery from. So if we had something like zinc and we reacted that with something like copper, and that made ZnCl2 plus copper, well, in this case, the Zn is actually going to Zn2 plus and losing 2 electrons. And those electrons are actually going over to Cu2 plus, grabbing them and doing that. Okay, and we can actually take the negative of this voltage value and add it to this voltage value to get the overall E cell, and this whole thing can be split up into a galvanic cell, with this being the anode and this being the cathode. The whole point being that we're trying to trap that transfer of electrons, that spontaneous transfer of electrons. In a battery like this, okay, one which is spontaneous, E cell is greater than 0 and delta G is less than 0. Similar to an equilibrium reaction where K would be greater than 0 for delta G to be less than 0. The next thing we moved on to was thermodynamics. And thermodynamics is governed by the laws of thermodynamics. And the first law saying that we have heat transfer, okay, or energy is transferred, and exothermic reactions are favorable. Okay. And the second law says that there's always disorder, and a positive change in disorder is favorable. And that can come together using the gotta hate this stuff equation. Okay. And it turns out that anytime you have these both paired up, anytime that this is negative and this is positive, the reaction is always going to be favored or spontaneous. So it's spontaneous always. Okay. If you have the opposite of this, it's spontaneous never. Okay. Now, if you favor one or the other, so let's say we favor the entropy but not the enthalpy, okay, we want this to win, so this is only going to be spontaneous as T increases, and let's say we favor the enthalpy, make that negative, because that's what we said here, but we don't favor the entropy, that's only going to be spontaneous as delta S loses, so as T decreases. Okay. Make sure here with delta S that you put it in kilojoules, but it's going to come in joules, so you got to divide it by 1,000. If you get it in kilojoules and want to report it, you need to multiply it by 1,000. Okay. And calculating this delta H can be a little tricky. I want you to remember that the bond's broken minus the bonds formed equals the delta H, left minus right. For 5, we talked about chemical kinetics. So this is the rate or the speed at which reactions happen. And that's based on something called collision theory. So I encourage you to watch that goofy video I sent you. And collision theory says that for a reaction to happen, it needs to have enough energy. And we call that energy the activation energy. And if you think of an energy diagram, the bond's broken, right? That's really the activation energy. Okay? And they don't just need the right energy, they need the right orientation. Okay. So we can look at 2 graphs to show this. We can look at an energy diagram showing reaction progress here. A goes to B. We'll make it exothermic. Okay. This is the energy in the forward direction needed to make it happen. And this is the energy in the reverse direction needed to make it happen. But this is only showing one successful reaction. If you get over that hill, you had enough energy and you had the right orientation. What we want to look at is we want to look at all the reactions happening. And to do that, we look at a Maxwell-Boltzmann distribution. So we look at the total number of particles and their energy. And it looks like a distribution. We're really taking this axis and plopping it here. This being the activation energy, and anybody who gets over the hill is right here. Okay. So these are the particles that have activation energy. Well, something that we really want to do in chem is we want to understand how to make that shaded region bigger. So let's look at a couple ways of doing that according to collision theory. So one way is we can increase the temp, okay, or decrease the temp. So the energy diagram would not change. Energy is going to look the same. But the Maxwell-Boltzmann distribution will, number energy. So if this is energy here, okay, if we increase the temp, it's going to shift it more this way. Okay. Subsequently, increasing the shaded region, increasing the average energy value. If we decrease the temp, it's going to look like that. Notice, in this case, we decrease the energy value. Another thing you could do is you could increase the surface area, okay, and increase the concentration, or increase the pressure. All of those things are going to do essentially the same thing. Again, they're not going to change the energy diagram. It still takes the same amount of energy to get over the hill, but they will change the Maxwell-Boltzmann distribution. Okay, where this is the activation energy, the shaded region, what they're going to do is it's going to keep the average energy the same, but just lift this up, effectively making it seem like there's more particles. You know, you're actually not just going from the outside, you're grinding it up, so you're getting on the inside with surface area. With concentration, you're just adding more particles, and pressure, you're basically adding more particles as well. So in this case, notice the shaded region increases in the Maxwell-Boltzmann distribution. And the third thing you can do is you can add a chemical catalyst. Okay, and if we add a chemical catalyst, we actually are changing this. We're changing the activation energy. We're adding a chemical that provides a new path. Spark plugs, things like that, those just provide the energy. They don't add a new path. So if you notice, we're not changing the shape of the curve, but what we are doing, if this is this EA, we're dropping this. So we're adding a lower EA. Okay. Now, rate order refers to how changing the concentration affects the rate. Zero order does not. That's always found in a faster step of a mechanism. Remember, to have zero order, you have to have multiple steps. First order showing a direct relationship, double, double, quadruple, quadruple, etc. And second order is showing a squared relationship, so double, quadruple, etc. Now, when we look at reactions happening over time, oftentimes we study how that particle is decaying over time. And it's important for you to know that in first order, the half-life, or the period of time it takes for it to cut in half, does not change. Okay, so study those graphs, understand half-life, and you should be good to go. But the concept is really grounded in this idea of collision theory, temperature being something we're using to change the energy, surface area, concentration, pressure, all changing the orientation or adding a chance that we'll have the correct orientation, and a catalyst, again, providing less energy. And the last thing we looked at throughout this year is chemical equilibrium. So chemical equilibrium is really nice. So let's say we have a reaction like 2A plus B goes to C. Okay, let's just say it happens in one step, a trimolecular collision. Okay, and over time, we want to plot this. And let's say you start here with like 2 here and 1 here and 0 here. So this is like 2A. A is going to be second order if this happens in one step. So we see the kinetics there. Here's B. B is going to be first order. And C is down here. C is going to be first order. Okay. So we need to calculate the equilibrium values. But first, let's talk about what's really going on here. First, this would be in molarity if we're talking about Kc. And it would be in atmospheres if we're talking about Kp. At the very beginning here, this is where the study of thermodynamics lies. Is delta G negative? Does it happen on its own once initiated? Here is where the study of kinetics lies. In this case, this is second order, non-constant half-life. You need to take 1 over A to straighten it out. The first one, that's B, constant half-life. You need to take the ln of B to straighten it out. And C is first order as well, and you would take the ln of that to straighten it out. And here is, we're still dealing with kinetics. I mean, think at the top is, does it happen? Here is when it's happening. And here is when the rate of the forward reaction is equal to the rate of the reverse reaction. So with equilibrium, we use this term con-re-equal. The concentrations are constant because the rates are equal. They're not the same. You could have this on the reactant side, and you could have this on the product side, okay? And in this case, K will be less than 1. It's going to be non-spontaneous, okay? But this is dumping here, and this is dumping here. The levels are not changing, but the rates are equal. So if you added a chemical catalyst to reaction at equilibrium, you're increasing the rate of the forward reaction, but you're also increasing the rate of the reverse reaction. So a chemical catalyst would not change the equilibrium concentrations, which we would find here. Okay. Remember, only aqueous and only gas particles count for equilibrium.